Hello and welcome to unit number 2. We're talking about probability in unit number 2. Our first topic of discussion is the binomial theorem. So, what is your goal today? I want you to be able to explain and apply the binomial theorem to algebraic expressions. So I'm going to show you a neat little shortcut to help with some expansions. So this is Pascal's triangle. You may have seen it already in the grade 11 course. And we see that the patterns that involve or that come out of the Pascal's triangle, you'll notice that there are ones on the diagonals, on the edges. And what then happens is that if we add these two numbers together, we get 2. If we add 1 plus 2 together, we get 3. 2 and 1 is 3. 3 and 3 is 6. 6 and 4 is 10. So it's easy for you to generate Pascal's triangle just by adding the one above. All right, so I'll just put up here, each term is the sum of the two terms above. Okay, so a couple things that I want to come out of you can take away from this. Let's look at the sum of each row. So I'm just going to shrink that, and maybe I'll put it up here out of the way. So I'm going to create a column here called sum. So I'm going to add up each row. All right. So the first row is going to have a sum of 1. 1 plus 1 is 2. 1 plus 2 plus 1 is 4. 6, 7, 8. Next one will be 16. Next one's going to be 32. The next one is 64. So I'm just going across and I'm adding these numbers together to find a sum. Okay? Now, if you look down the sum column, you can rewrite each of these sums as base 2. Oops, as base 2. So I'll do the easy ones first. So this is going to be 2 to the exponent 1. 2 squared is 4. 2 cubed is 8. 2 to the 4th is 16. 2 to the 5th is 32. 2 to the 6th is 64. And the top one, 2 to the exponent 0, gives us our 1. So finally, what we do is we call each of the rows inside Pascal's triangle row number. And when we deal with the row number, it starts with the exponent, or the exponent indicates row number. So row 0, 1, 2, 3, 4, 5, and 6. And I obviously went out of order there. Let's try that again. 1, 2, 3, 4, 5. Oops, sorry, I was right. And so there's your row number. So there's a couple things I want you to take away from Pascal's triangle. There's a ton of things that you get from Pascal's triangle, and that's just some of the key stuff that we need in order to move through this particular lesson. So, moving down, let's just talk about combination form for a second and how it relates to Pascal's triangle. So we know there's 4 forms to write a combination in. We have, oops, n choose r, so n combination r. Or you can write it as combination of nr, or you can write it as n factorial over r factorial n minus r factorial, or n choose r, no fraction, okay, that's the tricky part. All right, n choose r. Now, if we look at Pascal's triangle, and we use combinations, an interesting pattern occurs. If we plug this into the calculator, you don't really have to. I'm going to do it for us here. But if I do 0, choose 0, and then I do 1, choose 0, 1, choose 1, I'm only going to be able to fit a couple on here. 2, choose 0, 2, choose 1, 2, choose 2, and maybe I can squeeze one more in. 3, 0, 3, 1, 3, 2, 3, 3. If you were to plug those into the calculator, and I'll save you some time, 0 choose 0 is 1. 1 choose 0 is 1. 1 choose 1 is 1. 2 choose 0 is 1. 2 choose 2, or sorry, 2 choose 1 is 1, 2 choose 2 is 1, 3 choose 0 is 1, 3, 3, and 1. So what's kind of neat with Pascal's triangle is that those numbers, if you take a look at them, match up with the numbers from Pascal's triangle. So we can write Pascal's triangle as a series of combinations. So if we have n choose r, n is your row number, and r is your term number. Okay? So you can write the value, or find the value of each term inside Pascal's triangle simply by using combinations, knowing that if you want the third term in row 5, it's just going to be 5 choose 3. All right? And it becomes very important when we talk about binomial expansion. So binomial expansion, so recall from grade 10 and 11, and I'm going to zip through this. This is just a reminder. But if you wanted to do x plus y squared, remember that you have to write it twice, and then you have to, some of you learned FOIL, some of you learned distributive law. I'm going to speed it up and skip a step. So when you do that expansion, you get x squared plus 2xy plus y squared. For the next one, you would have to write it 3 times because it's cubed. And if you recall back to grade 10, at this point you're saying, oh my gosh, it's a lot of work. Yeah, it is a lot of work to expand it this way. So I knew that the second set of terms here, pen, so I know that x plus y times x plus y is just this from above. So I'm just building on it. Now I have to use distributive law here. FOIL doesn't work with you when you have more than 2 terms. And multiply that out. And if you do that expansion, you will end up with x cubed plus, then you're going to have 2x squared y plus 2x y squared plus yx squared plus 2x y squared plus 2y cubed. And there's some like terms in here. So keep in mind, this is not what you're going to be doing. I'm going to show you a shortcut, actually. Like term, like term, like term, like term. So I am just going to shrink that down. Oops. Group everything. Group, group, shrink. So that would give me x cubed plus 3x squared y plus 3x y squared plus, oops, shouldn't have been 2, should be just y cubed. You're probably saying, why is the 2 there? That's because I messed it up. So there we go. So in class, then I would be asking, if I would do this example, bring it up and say, okay, let's look at some of the patterns that develop in this expansion. And I'm going to tell you, you're going to have to, you can try it on your own, but I'm going to tell you what the pattern does continue. So what is one of the patterns that you see here? Okay, I can't see your hands, so don't put your hands up. You're watching a video. Come on, people. Think about it. All right, so what are the patterns? Well, if we look at the numbers in front of our variables, 1, 2, 1, 1, 3, 3, 1. Where have we seen this before? Well, Pascal's triangle, here to expand it out, and you can see how you just quickly can spin it up. If we look at Pascal's triangle, that first pattern that I had here, the 1, 2, 1, 1, 2, 1, it's right here, 1, 2, 1. So the coefficients in an expansion come from Pascal's triangle. And if you were noticing that, excellent work. If you didn't notice that, come on, pay attention. Number 2, what else do you notice? Well, if you take a look at, change to green, here I had a squared, and I had 1, 2, 3 terms. Here I had a cubed, and I had 1, 2, 3, 4 terms. So the number of terms is 1 more than the original exponent. All right. Next, what else do we notice here? What other pattern comes from this pattern or this expansion? You'll notice that the x squared term, it's the first term in the binomial. When we expand it, it starts with an exponent of 2, and then goes to 1, then disappears. The way we make that disappear is that it will go to the exponent 0. So if we take a look at the next one, 3, 2, 1, 0. So the first term starts with the original exponent. And decreases by 1 down to 0. Which means that now you're looking at the y term, the second term, and it does the opposite. The second term, the y, if you look at it, the second term starts at 0. And increases to the original exponent. Okay. Any other patterns that come from this? Well, if we look at the exponents themselves, do I have another color? Yeah. All right. So we know that that exponent 2 matches up with the original. We know that exponent 2 matches up with the original. If those exponents on the x and y are 1 and 1, the sum of them give me 2. Does that pattern hold? Exponent's 3, 2 and 1 is 3, 1 and 2 is 3, is 3. So the exponent, the fifth one, the exponent on the variables always sum to the original exponent. All right, so those exponents always add up to the original. So if you have originally to the exponent 2, they'll add up to 2. If it's 3, it all adds up to 3. All right, so what else can I tell you here? Well, row numbers are the only thing left now that I want to talk about. So this one will go 0, 1, 2, and 3. So if we're taking a row number, the coefficients, so if we go back to the coefficients right here, again, the coefficients stem from the exponent. So 2 and the term number, I'll put it under there, or row 3 and the term number. So what I'm saying is that really that 1, 2, and 1, 1, 2, 1 is the same as saying row 2, choose 0, 2, choose 1, 2, choose 2. So those coefficients, again, we can use the combinations where the top number, the exponent itself, tells you your row number. So exponent tells us the row number. All right, so we've picked out a bunch of patterns here, and this is going to help us speed up the expansion process. So next couple of videos, I'm just going to show you how you don't need to just use distributive law. You can just zip through it using this expansion and really do all these expansions in one step.